Hello, Beat from Not Just a Geek. Today I wanted to talk through the outcomes of our far infrared heating solution during the months of October and November 2022. October was a transition month where we installed the heaters and implemented the control system. We've set up heating with the following control scheme: a virtual thermostat for each room, implemented within Home Assistant. This takes the temperature from wireless thermometers in the rooms and uses a helper variable in Home Assistant as a switch. We then use automations with the relevant helper variables to control the relays corresponding to each heater. By doing this, we're able to differentiate the behavior of a request for heat from the thermostat and how we control the heaters. For our initial control scheme, we decided to set 1 kilowatt as the desired maximum heating power. This means that if 1 kilowatt or more was already being used for space heating, that a request for heat wouldn't activate a heater until another heater had gone offline. We'd set the units to cycle every 10 minutes, which provided plenty of opportunity for all heaters requesting heat to operate. Such an approach limited the draw from the heating system and allowed much of the power to be provided from the home storage battery or solar on good generation days. The current bit of clip shows the process in operation, though sped up. You'll note that when we're at 800 watts for one of the living room heaters, it is possible for another heater to activate, which will push us over the 1 kilowatt limit. However, once we have surpassed the 1 kilowatt limit, no more heaters can come on until a unit has been turned off. In addition to this, we implemented the idea of solar boosting, such that if there were excess solar, we would use it to heat rooms to a higher temperature than usual. Due to the nature of infrared heating, this effectively turned the fabric of the building into a storage heater, reducing the requirements for heating during cooler parts of the day. We engineered this system to prioritise north-facing rooms, since these would not benefit from solar gain as much as the south-facing rooms of the house. In the clip on screen, I've tweaked the control parameters to allow a higher power draw than 1 kilowatt to allow for more parallel operation. For reference, required power is the power required by everything in the house and deliberately excludes power going into battery charging. Battery charging is effectively the inverse of the required power, assuming, of course, that the battery is neither full nor completely empty. By having the required power exclude the battery, it is possible to enable turning on heaters, etc., when a certain boundary for excess electrical generation is reached. So, if we have an excess required power of 500 watts, minus 500 watts that is, then we'll put that into the battery because there's no appliances that would use that 500 watts. But as soon as it tips over to minus 600 watts, we might opt to turn on one of the smaller heaters. Looking at the data for October, we can see a mixture of different energy sources contributing to heating within the home. During this month we had significant boosting from the solar automation, which meant much of the fabric of the house was heated in the daytime from this excess energy. As a consequence, other energy sources played a less significant role. This is shown nicely by how closely the combined energy line tracks the solar energy line. In total, we used 119 kilowatt hours of energy for heating in October, 67% of which came from solar. The high level of solar boosting effectively enabled the entire fabric of the building to act as a storage heater, but it did mean that we used more energy than we would usually do for heating, because we probably wouldn't have bothered to put that extra energy in otherwise. Carbon emissions wise, the grams per kilowatt hour have been kept very low due to the percentage of solar heating, roughly 41.8 grams per kilowatt of heat. This compares very favourably to a modern gas boiler, which would be closer to 215 grams per kilowatt hour. In the month of November, we used more energy for heating, which isn't too surprising as it was a bit colder, 265.17 kilowatt hours. Of this, 67 kilowatt hours came from solar. The solar figure isn't particularly different to the October figure. However, given the higher energy consumption, it means that the percentage of heating from solar was 24% rather than 67% in October. From the graph, we can see that off-grid and battery energy provided most of the remaining energy for the month. For the sake of simplicity, I'm treating battery energy as off-grid, though some of it certainly came from solar in the month. In terms of carbon emissions, the grid was, any energy we imported from the grid was at 153.5 grams per kilowatt hour, whereas the heating itself worked out 117 grams of CO2 per kilowatt hour, again due to the boosting in solar heating. Both these figures would compare well with a gas boiler. In a future video, I'll compare the actual energy usage of both the gas boiler and the electric heaters, as we found that there is a roughly 40 to 45% reduction in energy required for the far infrared versus gas, which obviously makes these figures even more competitive. Similarly, I'll spend some time outlining how prices might work. Thank you for watching, and I'll upload another one soon, hopefully.